I'm Chen from Arizona State University, and the work I'm going to present today is FASCINATE. That is fast cross-layer dependency inference in multi-layer networks. And it's a joint work with my advisor, Han Tong, and Professor Lei Xie, Professor Lei Ying, and Professor Qing He. So actually, multi-layer networks are actually everywhere around us. It actually is a powerful data structure that describes the connections and the dependencies between different kinds of entities. So it has two major components. The first component describes the connections between same kind of entities. And the second component is actually cross-layer dependencies that describes the dependency relationship between different kinds of entities. So to help you form a general idea about what is multi-layer network, here we give three basic typical examples, and they are infrastructure networks, collaboration platforms, and biosystems. We can take a close look to the biosystem example. So here we have 4 layers. And for example, in the chemical layer, the nodes here are different kinds of chemicals. And the link in this network is actually describe the similarities between different chemicals. So similarly, we have drug network, a disease network, and protein-protein interaction network. But between those layers, we know that chemicals actually is the main composition of drugs. Well, drugs is used to treat a different kind of diseases. And diseases is actually associated with to a certain kind of proteins, which is a node in the PPI network. So as you might have noticed, actually cross-layer dependencies is actually the unique topology characteristic of multi-layer networks. For example, in our infrastructure network example, the power grid is always needed to provide power to make the autonomous system and the transportation network work. And the autonomous system, in turn, is needed to provide control mechanisms to power grid and the transportation networks to keep it working order. And for some coal-fired power stations, working transportation network is also needed to provide fuel to it. So actually, cross-layer dependencies is key to many multi-layer network mining tasks like connectivity control and the system robustness analysis. But the key challenge here is that in most of the multi-layer networks, the observed cross-layer dependencies are often incomplete due to noise or incomplete records or network dynamics. So in other words, the observed cross-layer dependencies are often incomplete. Still, again, we take the previous 3 examples. In the infrastructure networks, when a disaster like tornado would significantly disrupt the power grid and its related dependencies. So in this case, it will also make people have limited access to the epicenter. So in this way, we'll only have a coarse-grained description about what kind of cross-layer dependencies are still remain working in these systems. And for the biological system, for some drugs in the biological system, their effects to some diseases would remains unknown because there might be some regulation policies or limited budget issues. So give those examples here, it's natural to give rise to the question that how to infer the hidden cross-layer dependencies in those multi-layer systems. And another common problems in the multi-layer networks is that new nodes are keep emerging over time. For example, when a new router is added to an autonomous system in the infrastructure network, a new employee is hired by a company, or a new disease is discovered in the biological system, their cross-layer dependencies may always will be completely unknown. So in this case, how can we efficiently infer their dependencies across layers is also an important question. So here we'll start to address the first question, that is cross-layer dependency inference. Before we start, we can take a short detour about the background, that is a multi-layer network model. So given a multi-layer network, it can be actually represented by a tuple, G, A, and D. G is actually the layer-layer dependency network, and A is a set of matrices that describe the intra-layer connectivities. And D is a set of matrices that describe the cross-layer dependencies among different layers. So in our four-layered network here, it can be abstracted into a layer-layer dependency network with 4 nodes. And the nodes in such kind of abstracted work is actually the intra-layer the adjacency matrix of the corresponding intra-layer network. And the edge in the abstracted network is the node-level cross-layer dependency matrices. So to address the dependency inference problem, our key idea is to make analogy to collaborative filtering problems. So suppose we are giving a two-layer multi-layer network that has routers and transportation networks, transportation vehicles, and we only have the dependencies between routers and the vehicles. Then in this case, the problems of inferring cross-layer dependencies can be viewed as a problem of recommending movies to the users in a recommender system. So here, the users can be viewed as routers. Movies can be viewed as vehicles in the transportation networks. And the observed ratings in the recommender system can be viewed as the observed cross-layer dependencies. So by the mechanism of collaborative filtering, the user rating matrices, or equivalently, the cross-layer dependency matrix, can be factorized into the product of 2 latent feature matrices. So when this system becomes, when more information comes to this system, like when the connections between routers and links in the transportation network was added to the multi-layer network, we can view it as a recommender system with social network informations and movie similarity informations. So in this case, the movie similarity can be viewed as a link in transportation network, and the link between users can be viewed as the connection of routers in the autonomous system network. So to exploit the side information in intra-layer networks, our basic assumption is that closely connected entities within each layers tend to have similar latent profiles. So that implies when user 1 and user 2 are closely connected to each other as friends, they may have similar idols and like similar kinds of movies. So since they are similar in the multi-layer networks, suppose if 2 routers are closely connected to each other, then probably they will control similar sets of vehicles in the transportation network. So when the whole system begins to become even more complex, we can extend the previous analogy by considering the impact of celebrities into the recommender system. So in this case, we can view the celebrities as power plants because they actually are the motivations for their fans to watch the movies. And also, they are the core part of the movies they act in. And the users can actually be viewed as routers because they actually determines the popularity of the celebrities and also determines the box office of certain kinds of movies. And also, movies can be viewed as transportation networks because somehow they will determine the popularity of the celebrities too. So putting all the previous things together, we can model the cross-layer dependency inference problems as optimization problems with the following objective function. This function actually have three parts, and the first part is used to match the inferred cross-layer dependencies with the observed ones. And the second term is used to fit the node homomorphy assumption. And the last term is just a regularization term to avoid overfitting. But the biggest challenge here is that this objective function is not jointly convex with all the latent feature matrices. So the key problem here is that we can't find it's hard to find a global optimal solution for that. So the question here instead is that how can we find a local optimal for that? To solve the previous problems, we propose FASCINATE. It's based on our observation that is the previous objective function will become convex if we choose one latent feature matrix to optimize and fix all other matrices. And in this way, we can find a local optimal solution by block coordinate descent method. That is, we optimize each latent feature matrices alternatively. And the following function gives the simplified objective function with respect to the latent feature matrix Fi. And you can see it is only related to layer I and its dependent layers. And to solve this objective function, we can use multiplicative update rule. And it is listed here. So we can proceed to the second question, that is inferring the dependency of zero-star nodes. So suppose there was a new power station that added to the power grid. Then the adjacency matrix of power grid will be extended by adding a new row and a new column to its matrix. And consequently, the latent features of the nodes in the whole systems will be updated. Specifically, for the nodes in power grid, it can be decomposed into two parts. The first part is the updated latent feature of the existing nodes. And the second part is the latent feature of the new nodes. And correspondingly, we can decompose the previous objective function into two parts as well. And the first part is actually the previous objective function without the zero-star nodes. And the second part is a function that is only related to the newly added nodes and its local neighbors. So as you can see, usually a multi-layer network is a huge system. When only one new node is added to the system, the perturbation caused by these new nodes will be very small compared to the whole system. So we can hold a local search assumption. That is, for all the existing nodes, their latent features would remain almost the same after the perturbation. So in this case, the objective function can be simplified to a term that is only related to the zero-star nodes and their local neighbors. And by solving this function, and it is also convex to the latent feature of the new nodes, we can see that it's actually the weighted average of zero-star nodes' local neighbors. So to evaluate our method, we have done our experiment on 4 different data sets. One of the data sets is actually a social collaboration platform. One of them is the biological system, and the other 2 are real infrastructure networks. Our evaluation objectives to show how accurate and fast is our proposed FASCINATE algorithm. So to evaluate the effectiveness of FASCINATE algorithm, we have experimented on all 4 data sets. And as you can see from this table, this is from the biological system data set. This is a result from biological data set, but we observe similar results in other data sets too. And we can see that our proposed FASCINATE algorithm performs best over all the best competitors. And also, we have studied how the weights of node homomorphy term and regularization term and the rank of latent feature matrices would affect the performance of FASCINATE. And as you can see from this figure, our proposed algorithm is performs stable in a wide range of parameter settings. So we have also evaluated the effectiveness of FASCINATE 0 for the 0-star nodes. And we have here compared the mean average precision of FASCINATE 0 with FASCINATE under the same experiment settings. As you can see from this figure, FASCINATE 0 can achieve similar performance with FASCINATE, but with orders of magnitudes faster speed. And last, we have studied the scalability of our proposed algorithms. Consistent with our previous complexity analysis, we see that FASCINATE scales linearly with respect to the network size, and FASCINATE 0 scales sublinearly to the size of the overall system. So to conclude, in our paper, we have addressed the problem of cross-layer dependency inference. And our key idea is to make an analogy to collective collaborative filtering problem. And by the node homomorphy and the local search assumptions, we propose the FASCINATE and FASCINATE 0. And our experimental result shows that our proposed algorithm can achieve up to 40% of improvement of the best competitors. And it actually scales linearly for FASCINATE and sublinearly for FASCINATE 0. And OK, thank you for listening.
Very nice work. I was wondering, on slide 14 or 13, I was wondering whether you can easily generalize your method to handle not only homophily, but everything else, right? Yeah, so the green equation, homophily, I think it could be easily extended to heterophily and any other compatibility matrix, right?
Yeah, yeah. It can be extended to other like methods to explore the information in the intralayer networks. Yeah.
For the models that didn't do as well, did they not take all of the variables into account, or did they not use the fact that they happen at different layers? Do you know? I guess I'm trying to ask, like, what do the layers add the most? Like, yeah, it's clear that you can do inference when you add, but what does it add? Because you're losing some kind of information, right? Because you're collapsing things.
We didn't collapse things because layers are separate to each other, and we are measuring the dependency pairwisely.
But if you just treated everything as being on the same layer, how did the results change?
It's different layers. But we have made some experiment to flatten the overall system into a large graph. Yeah.
And does that do worse?
We actually have the experiment result here. It's one of the baseline algorithm here.
Okay.
So you can see like a flattened NMF is actually the performance of if we flatten all the layers into one large network. And it did not perform very well compared to our algorithm.
So to sort of finish that question, is the insight why other methods did not perform as well compared to yours? What does yours explicitly, which concept allows you to perform that well?
Yeah, I think the main thing here is that our model can collectively consider the dependency information between each layers. For the comparing models, like you can see the mole code in the first line of the baseline method. We have for this method we have changed the homomorphic term actually into a simple approximation of the intra-layer network agency matrix, and it does not perform very well because I think node homomorphy plays an important role in these problems. And for other methods, like the method starts with pair, it only consider the pairwise method in the system, but it does not consider the collective method of other layers in the dependency matrices. So that's why they don't work. And for the flatten method, as you can see, it's not working very well if you flatten into a large network.
Thank you. Any other questions? There. Last question. Okay.
Yep. So I have a question about how you define the interlayer dependencies. So for example, I'm not sure about this case, but for example, in the electricity case, like for example, if you're like a city A is powered by station A, and then station A is connected by station B, then of course like there is some electricity flow coming between station A to station B, but there may be like only one directed, like one hub dependency from station A to the city. But there's actually some inherent dependency from station B to the city as well because the electricity flow. So in the BIOS data set, like what kind of dependencies are they considering in that case?
Currently, they only consider node level.
Like a direct dependency.
Yeah.
I see.
Yeah, but I think like indirect dependencies can be inferred by the collective model.